So let's take a look at example 3, part 2. In part 2, we're doing the same thing we did in part 1, except it's just got 3 different variables instead of 2 variables. So, you know, whatever, it is what it is. So the first things first, here's what I would have done in the past. In the past, I would have said I want an integral for the x squared, I want an integral for the x, and I want an integral for the 6. Then I would say I'd like to get the numbers out of the integrals. So the x squared stays alone, the x is left alone, and the 6 exits the integral because it's a number. Then we integrate each one of them one by one. So the x squared becomes x3 over 3 because adding 1 and dividing by the same thing. X to the power of 1 becomes x squared over 2, and the 6 becomes 6x because we're integrating nothing. That means we're integrating 1. So typically speaking, that's what you do. Now you could do all that stuff mentally at this point since we've been doing it for a while, and just record the answer over here. X cubed over 3 minus x squared over 2 plus 6x. Difference is we have to put the 0 and the 2. Why 0 and 2? Because the upper bound is 2 and the lower bound is basically 0. And now we just have to make the adjustments and plug in the upper bound, plug in the lower bound, and subtract the 2 answers. So this is how it's going to look like. You're plugging the 2 into all the x's. You get 2 cubed over 3, 2 squared over 2, and then 6 times 2. Then you plug in the 0 into all the x's. 0 cubed over 3, 0 squared over 2, and then 6 times 0. And now don't bother doing all this stuff by hand. It's just, too much work to do by hand. Just plug all of the stuff into the calculator and tell me what your answer is. So 38 over 3 is the final answer. So pretty straightforward. I would highly recommend that you try to use your calculator to get the answer 38 over 3. Make sure that you get the right solution. And that's pretty much it. It's pretty simple, no? The same strategy works even if you have exponentials. Like for example, in this problem, we have exponential 0 to 1 e to the power of x plus x. So again, how do we work out these problems? So 0 to 1, e to the power of x plus x. Well, I'm going to pretend like I have just e to the x and x without the 0 and 1. What would I do if I had just e to the x plus x? Well, normally what I would do is I would give an integral for each one of them. E to the x gets its own integral, and then the x gets its own integral. But the antiderivative for e to the x is literally e to the x. It does not change. And the antiderivative for x is x squared over 2. Because x to the power of 1, you add 1 to the exponent and you divide by the same thing. So now that I have the antiderivative, I'm just going to grab the answer that I got and write it over here. E to the x plus x squared over 2. And what I have to do next is plug in the 0 and the 1 into my problem. Okay, so remember the 1 is the upper bound, 0 is the lower bound. 1 goes in first, and you get e to the power of 1 plus 1/2. And then the 0 goes in, and when the 0 goes in, we get e to the power of 0 plus 0 squared over 2. Okay, so as usual, we plug the upper bound first. That's why I'm plugging in the 1 into all the x's. Then we plug in the lower bound. That's why I'm plugging in 0. Now, if you try to plug this into your calculator and make it into a fraction, there's no way on earth it's going to become a fraction. That's because e right here, by definition, is irrational. It cannot be written as a fraction. So unfortunately for this one, you have to do it by hand. There is no calculator here. I mean, you can get a decimal on the screen, but that's not very useful because MyMathLab most of the time wants an exact answer. So what you're going to do is this. E to the power of 1 is just e. And remember, e is roughly 2.7, whatever. Plus 1 squared, that's going to be 1. Minus e to the power of 0 is basically 1. Anything to the power of 0 is 1. And then finally, 0 squared divided by 2 is going to be 0. I'm not going to even bother writing it. And so this is going to mean that these two right here are like terms. So they're going to combine together. And when you combine them together, the solution becomes 1/2. So my final answer is e minus 1/2. So roughly speaking, this is 2.7. This is 0.5. So roughly speaking, the answer is going to be around 2.2 basically. Now, again, your screen shows you 2.2, but it's not going to be able to turn it into a fraction. That's because e is irrational. So you have to do the process of evaluation by hand. I hope that made sense. Let's take a look at the next one. It says x plus 2 divided by x, integral from 1 to 4. So again, integral from 1 to 4, x plus 2 divided by x dx. First things first, integrate it without the numbers. So think about what would I do if I had x plus 2 divided by x dx. And what I would do for these problems is I would write each one of them separately with its own denominator. So I get x over x dx, and I get the 2 over x dx. And then I would reduce each of the fractions. X over x is 1 dx. And for this one, I'm just going to pull the 2 out of the integral. So it's going to be 2, nothing left on top. So I'm going to put a 1 over x dx. And we integrate term by term. So the 1 turns out to be x. Antiderivative of 1 is x. And then for the 1 over x dx, there's a formula that says ln of absolute value of x. So that's the antiderivative, okay? That's typically the hardest part of the problem. Once you get that done, it's very straightforward afterwards. So in any case, now that we have the antiderivative, I'm just gonna grab the answer, x plus 2 ln absolute value of x, and put the little bar next to it with the 1 and the 4. So this means 4 is going to go next into the problem, into all the x's. So when I do that, I get 4 instead of the x, plus 2 ln absolute value of 4. So this is what I get from plugging in the upper bound in the problem. 4 goes into all the x's. Then we subtract the lower bound. The lower bound is 1, so 1 plus 2 ln of absolute value of 1. 1 is the lower bound, that's why I'm plugging it in. Sorry, I use a different color every time. Let me stick with the same color. Blue for the lower bound. Okay, there you go, there it is. Again, if you try to plug this into the calculator, it's gonna be a decimal and it's not gonna turn into a fraction. So unfortunately for this problem, we have to do it by hand. So the 4 is gonna hang out. The 2 ln of absolute value of 4. Absolute value of 4 is gonna be just 4. So we can write down 2 ln 4 without the absolute values. We can make it just regular parentheses. Negative 1, and then negative times positive is going to be negative 2 ln of 1. Now you can test this out in your calculator. You can find out that ln of 1 is actually 0. So the value of ln of 1 is 0. 0 times 2 is going to be 0. So this whole thing will not count. So we're left with basically these 3. And out of those 3, there are 2 like terms. The 4 and the negative 1 are like terms. So when you add them, you get 3 plus 2 ln of 4. And unfortunately, the 2 has an ln next to it and the 3 does not. So there's no like terms left. So that's pretty much the solution right there. Again, the calculator is not able to make that into a fraction. So whenever you get one of these answers with ln or e, you have to work it out by hand. So to summarize what we just did in the last few problems, like I said, this is called the fundamental theorem of calculus or integral calculus. This is a super important theorem in mathematics. It's probably going to be the one thing that you will need to remember out of this whole class that we're taking together. It's a really, really serious, important problem. And it basically says to find the answer to one of these definite integrals, do an antiderivative, then plug in the upper bound and lower bound and subtract the answers. That's what the theorem basically says.